Up to this point, we learned several things. First, from the quantum mechanical point of view, the position of a particle is not an exact point in space. It is defined by the probability distribution, which itself is proportional to the square of the wave function of this particle. Second, the probability for a particle to be detected in some area is proportional to the integral of its wave function square of over this area. And third, for the particle to exist somewhere in space, the integral of the wave function square over the whole space must be non-zero and finite. Now please note that I say proportional, not equal, when I talk about the integral of the wave function square and the probability. Let's take a look at the graph of some function. The integral of this function over the whole space equals to some value a, which is finite and non-zero. Does this graph represent some probability distribution? To answer this question, we have to ask if the value a is equal to 1, because for a well-defined probability distribution, this integral has the meaning of the probability of the sure event, which is 1. But if the value a does not equal to 1, there's still a way to make this function to be the correct probability distribution. You can just divide it by a, and the resulting function will have the integral equal to 1, thus being the correct probability distribution. This procedure that we perform to make the positive valued function to be the correct probability distribution is called normalization. Why do we need it? Well, because we want the wave functions to form an infinite-dimensional vector space. Let's recall what a vector space is. First of all, the vector space, let's call it F, is a set, which means it has elements. The elements of this set we are going to call vectors. The set is called a vector space if 1. We can multiply any of its elements by a number, and after that, the resulting element must still belong to this set. The numbers we consider here can be different. If we define this procedure only for real numbers, we will say that we have a vector space over the set of real numbers. If this procedure is defined for complex numbers, we will say that we have a vector space over the set of complex numbers. And second demand for a set to be a vector space is we can add up two different elements of F and obtain another element of F, which means we have to define a procedure called plus on this set. For example, the arrows on the plane, which all begin at some initial point, form a vector space over the set of real numbers if, first, we define the multiplication of an arrow by a scalar as the same arrow with its initial length multiplied by this scalar. And second, we define the sum of two arrows as the diagonal of a parallelogram defined by these arrows. Okay, for some reason, not quite obvious for now, we want to define a vector space F on the set of wave functions. To do this, we have to define these procedures. For example, we have some wave function f. Let's assume that the integral of its square over the whole space is equal to 1. Thus, it is square-integrable, and it defines a correct probability distribution. Then we can say that this function f can have a physical meaning. It can define the position of some particle in the quantum mechanical sense. Okay, what happens if we multiply this function by a scalar, which means a number, a? I don't specify yet what kind of a number a is. Is it a real or a complex number? Let it be real for now, for the sake of clarity. Then the resulting function remains square-integrable. The integral of its square is still finite. But this integral will be also multiplied by some number b, which is the square of the value a. And now, for the resulting distribution to be correct, we have to normalize it, which means to divide it by b. And after it, we obtain exactly the same probability distribution as before, having the same physical meaning. So, after introducing the mandatory normalization procedure for our probability distributions, we obtain the possibility to multiply square-integrable functions by scalars. And all such functions still have a physical meaning for us, since we know now how to obtain the correct probability distribution out of any of them. I want to stress here a very important effect of introducing the normalization procedure. For any well-defined wave function f, multiplication of it by any scalar, except 0 of course, does not change its physical meaning. For any scalar a, f multiplied by a physically represents the same state of the particle. Now we have to define the sum of two square-integrable functions. It will be just the usual sum, which means that for functions f and g, the resulting function f plus g at some point x equals to the sum of functions' values at this point, f of x plus g of x. And since these both functions f and g are square-integrable, one can easily show, though we are not going to do that, that their sum defined this way is also square-integrable. Okay, we have constructed the vector space of wave functions. And as you probably remember, in any vector space you can choose a basis. Basis is the set of vectors, usually they are the elements of the considered vector space, which generate the whole space. It means that any vector from this space can be represented as some weighted sum of these vectors of the basis. There are infinite number of bases you can choose for the same space, but all of them share one important parameter. They all have the same number of elements. The number of elements of the vector space basis is called the dimensionality of the space. In our previous example with arrows on the plane, we can choose different bases, which are marked with different colors here on the picture. I have drawn only two of them, but there are infinitely more. I'm just too lazy to draw infinite number of bases to demonstrate this simple point. The important thing here is that the vector space of arrows on a plane has the dimensionality equal to 2, since each its basis has exactly 2 elements. Another important thing I wanted to show on this picture is that there are special kind of bases, which are called the orthonormal bases. These are the bases which elements has the length of 1 and are mutually perpendicular to each other. The basis shown in green on this picture is orthonormal. These orthonormal bases play an important role in quantum mechanics, which we are going to discuss later. Now, what is the dimensionality of the vector space of square-integrable functions? It is well known from mathematical analysis that for this space the number of dimensions is infinite, which means that any basis we will choose will have the infinite number of elements. Okay, enough for now about the space of the wave functions. Let's talk about their measurement.